everyone, and welcome. If you're an engineering student, listen up, because we're about to add a seriously powerful set of tools to your future toolkit. Today, we're going to build a solid foundation for understanding artificial intelligence and machine learning, not as some abstract sci-fi concept, but as real-world tools for building smarter systems. Let's get right into it. So, when I say AI, what pops into your head? Probably a chatbot, right? Or maybe some kind of robot from a movie. And hey, that's totally fair. But it's also just scratching the surface. The real AI revolution, the one that's going to change your career, is happening somewhere else entirely. Here's the key idea I want you to remember. AI is all about taking the physical systems we design, everything from a massive turbine engine to a tiny embedded chip, and giving them a brain, giving them the ability to see, to learn, and to adapt to the world around them. It's about embedding intelligence right into the hardware you're already building. Okay, so to really wrap our heads around that, we need to start with the basics. Let's get on the same page and nail down our core definitions. What are we actually talking about when we say AI versus machine learning? When you boil it all down, artificial intelligence is the big picture goal. It's the whole field dedicated to making machines do things that, if a human did them, we'd say requires intelligence. You know, things like reasoning, making plans, or just understanding what's going on. AI is the mission. Teach a machine how to think. So if AI is the what, then machine learning, or ML, is the most important how we have today. It's this incredible part of AI that totally flips programming upside down. Instead of us sitting there and writing a million lines of code for every single possible situation, we build systems that learn the rules themselves, just by looking at data and experience. And believe me, this idea has been on a wild ride. It really kicked off in the 50s, more as a philosophy question than anything. Then, in the 70s and 80s, we got these things called expert systems, where engineers literally tried to hard code all human knowledge into a machine with rigid, logical rules. But, well, reality is messy. The hype got way ahead of the results, funding disappeared, and we hit these periods called the AI winters. Then, in the 2000s, everything changed. We had this perfect storm of massive amounts of data, super powerful computers, and a huge shift towards learning from that data instead of just using rigid rules. And that brings us to today. And that's why that history lesson is so important for you. That whole evolution from fixed logic to adaptive learning, it's the exact same shift that's happening in your field. It's the jump from a simple, pre-programmed control loop to a smart, adaptive system that can actually optimize itself in real time. It proves that algorithms are only one piece of the puzzle. It's the hardware and the data that really unlock the magic. All right, so we know what it is, but let's get specific. Why should a mechanical or computer engineer really care about all this? And how is it different from another buzzword you hear all the time, data science? Let's clear that up right now. You know, people tend to use these terms interchangeably, but they have totally different goals. Think of it this way. Data science is all about analyzing data to find insights that help a human make a better decision. The final product is often a report or a dashboard. AI, though, uses those insights to let the machine itself take action. The output isn't a report, it's an autonomous system, making its own decisions out in the world. And this is where it gets really exciting for you. In your world, this isn't some abstract theory. It's predictive maintenance, using sensor data to know a gear is going to fail before it actually does. It's a robot on an assembly line that can actually see a part that isn't perfectly aligned and adapt on the fly. And for all you computer engineers, it's Edge NI, running these powerful models directly on the hardware you design, like FPGAs and systems on a chip, right where the action is happening. Since machine learning is the engine that's driving so many of these amazing new systems, we've got to pop the hood and see how it works. Generally, ML gets broken down into three main approaches. Let's take a quick look at each one. First up, we have supervised learning. And the analogy here is just perfect. It's like studying for a test with the answer key. You feed the algorithm a ton of data where you've already labeled the correct output. So, for example, you give it thousands of hours of vibration data from an engine, where every little piece is already tagged as either normal or about to fail. The model just learns the patterns that connect the data to the label so it can make that call on its own next time. But what happens when you don't have an answer key? That's where unsupervised learning comes in. It's awesome. You just give the model a whole sea of unlabeled data and basically say, find something interesting. Its job is to find the hidden structures, the clusters, the weird outliers, all on its own. This is how you discover a totally new type of fault in a machine, one that no one has ever even seen before. And last but not least, my personal favorite, reinforcement learning. With this one, you have an agent, say a robotic arm, that learns through pure trial and error. It tries to do something, and if it does it well, you give it a reward. If it messes up, you give it a penalty. After millions and millions of tries, it figures out the absolute best strategy to get the most rewards. This is exactly how we can train a robot to assemble something way faster and more accurately than any human ever could. Okay, let's zoom out for a second. All these different ways of learning kind of fall into a bigger picture. If you look at the history of AI, there have really been two main schools of thought on how to build an intelligent machine. Two different minds, if you will. On one side, you've got symbolic AI. Think of this as the logician. It works with explicit rules that a human programs in, like if the temperature is above X and the pressure is above Y, then trigger the alarm. It's easy to understand and great for tasks with clear rules. But it's brittle. It breaks the second it sees something new. On the other side, you have sub-symbolic AI. This is the pattern finder. This is the world of machine learning and neural networks. It learns from messy data without any hard-coded rules. The absolute best systems we have today are actually hybrids. They combine the strict logic of one with the flexible learning of the other. So when you start mixing and matching these different approaches, you end up building systems that have these 7 core capabilities, the essential ingredients of intelligence. You get things like reasoning and planning from that symbolic side, and you get learning and perception from the sub-symbolic side. And for you mechanical and robotics engineers, it all comes together in those last two, motion and manipulation, the ability to physically act on the world. So after all that, what does this actually mean for you as you get ready to start your career? Well, it means your engineering toolkit just got a massive, massive upgrade. And listen, if you take away only one thing from this whole explainer, make it this. AI is not coming for your job. It is a force multiplier. It's a tool that will let you design and build systems that are smarter, faster, and more adaptive than we ever thought possible. The engineers who learn how to use this tool, they're the ones who are going to be building the future.